Conversational AI multi-agent interoperability frameworks are crucial for efficient and effective interactions among diverse agents, including chatbots, voicebots, videobots, and human agents. The Open Voice Interoperability Initiative proposes a novel architecture, OVON, which establishes and enables interoperable interactions among agents through universal APIs based on natural language. This framework introduces a discovery specification framework for efficient lookup of agents providing specific services and obtains accurate information about these services through a standard manifest publication, accessible via an extended set of natural language-based APIs. The proliferation of chatbots and voicebots, with over 200,000 available worldwide, necessitates a standardized framework for interoperable interactions. Current conversational AI interactions are becoming pervasive, with an increasing number of interactions occurring directly among AI agents themselves. However, the lack of an interoperable framework leads to implementation complexity, duplication of effort, and user frustration. The Open Voice Interoperability Initiative aims to mitigate these issues by defining interoperable standards for conversational AI agent interactions. Previous work on enabling independent conversational assistants to exchange information includes approaches such as independent modality components collaborating through standard APIs, independent assistants collaborating through hardwiring at development time, and systems supporting interaction among independent assistants. However, these approaches have limitations, such as requiring all collaborating assistants to be known ahead of time, familiarity with specific APIs, and a common technology base. In contrast, the OVON architecture enables conversational assistants with any internal architecture to collaborate as long as they adhere to the communication standards. The framework introduces a discovery specification framework, which efficiently looks up agents providing specific services and obtains accurate information about these services. The main purpose of this contribution is to significantly enhance the capabilities and scalability of AI interactions across various platforms. The rest of the paper is structured to describe earlier related work, an open-source approach to intelligent assistant interoperability, state diagrams illustrating the lifecycle of an exchange among interoperable agents, and detailed use cases. The paper also reviews future directions and conclusions. The Open Voice Interoperability Initiative's work differs from previous approaches in that it makes fewer assumptions about the internal structures of the assistants, allowing for greater flexibility and scalability in conversational AI interactions. The researchers present a novel approach to conversational AI interoperability, enabling independent assistants to work together seamlessly. Unlike previous work, this approach allows assistants using different technologies and channels to collaborate with minimal requirements for integration. The Open Voice Conversation Envelope API facilitates this collaboration, passing user requests to secondary assistants that interpret natural language. The researchers compare their approach to three other methods: independent modality components, agentic hardwired collaboration, and interagent communication language. Their approach stands out for its loose coupling of assistants, supporting various technologies, and minimal requirements for integration. The Open Voice Interoperability Initiative has released the first version of the Interoperable Conversation Envelope specification, which enables agents to send events to each other, carrying information about utterances, whispers, invites, buy messages, and manifest requests. These events are standardized, allowing agents to communicate effectively, regardless of their underlying architecture or technology. The specification draws no distinction between human agents and automated agents, anticipating that language-capable AIs will interact with each other in the same way as humans cooperate. The framework enables agents to initiate requests or respond to requests, forming chains and trees of agent interactions. The researchers propose using state diagrams to model the behavior of AI agents, illustrating their states and transitions based on specific events or conditions. This representation is useful for mapping the OVON interoperability specifications to the dynamic statuses and standard messages exchange. The state diagrams shown only describe states relevant to interagent collaboration, excluding internal states not concerned with interoperability. The researchers' approach is motivated by three premises: the ubiquity of foundation language models leading to multiple specialized conversational agents, the need for these agents to collaborate to achieve tasks, and the potential for this collaboration to be based on unstructured natural language. If these premises prove correct, there will be a need for interoperability between AIs using different underlying architectures and technologies. The paper discusses the concept of conversational AI agents, focusing on their roles as serving and demanding agents. A serving agent is an AI entity designed to provide services, information, or assistance to users or other agents, while a demanding agent initiates requests or tasks, seeking services, information, or assistance from other agents or systems. The authors present the OVON, Open Voice Network, conversation envelope, a universal JSON structure that allows human or automatic agents to interoperably participate in a conversation. They provide state diagrams illustrating the different states and transitions related to both serving and demanding agents during normal and unsuccessful conversations. In a successful conversation, a serving agent moves from the idle state to the ready state upon receiving an invite event, then to the searching for response state upon receiving an utterance or whisper event. Upon successfully finding a response, the agent moves to the sending response state and sends the response to the demanding agent, returning to the ready state for further interactions. If the conversation is terminated, the serving agent returns to the idle state. In an unsuccessful conversation, the serving agent moves from the idle state to the ready state, then to the searching for response state, but fails to find a response. This results in the conversation being terminated, and the serving agent returns to the idle state. For a demanding agent, the process starts with the idle state, moving to the ready state upon sending an invite event. The demanding agent continues sending utterances or whispers and moves to the consuming response state upon receiving a response from the serving agent. From there, it can return to the ready state for further interactions or terminate the conversation and return to the idle state. These state diagrams and their explanations provide a comprehensive understanding of how conversational AI agents interact and manage conversations, highlighting the roles of serving and demanding agents in maintaining a smooth flow of information exchange. Interoperable assistant manifest diagrams enable agents to describe their capabilities to other agents, facilitating a discovery process for agents with specific capabilities. The state diagram in Figure 5 illustrates the states and transitions related to a demanding agent looking for the manifest details of a target agent. From the capability search state, the agent moves to the waiting for manifest state upon sending a request manifest standard message envelope event. The agent can continue sending request manifest periodically or move to the ready state upon receiving a response from the serving agent via the publish manifest standard message envelope event. In cases where the potential serving agent is unknown, a natural language-based API similar to Whisper events can be used to search for a list of potential serving agents capable of accomplishing specific tasks. The state diagram in Figure 6 shows the different states and transitions related to a demanding agent looking for assistance available to perform specific tasks. From the assistant search state, the agent moves to the waiting for assistant list state upon sending a find assistant standard message envelope event. The agent can continue sending find assistant periodically or move to the ready state upon receiving a response from the serving agent via the propose manifest standard message envelope event. The Smart Errands use case demonstrates the interaction of multiple agents coordinating and optimizing a series of errands according to the Universal Open API specifications for Agentic natural language multimodal communications. Emmett, a human, interacts with Cassandra, his general AI assistant, to manage and streamline his errands efficiently. Cassandra facilitates transactions with AI assistants at various service points, including Pat at Bloomingtown Florist, Andrew at the post office, Charles at the hardware store, and Sukanya at Thai Palace. The conversation between Emmett and the AI assistants illustrates the use of natural language-based APIs to search for agents capable of accomplishing specific tasks and to coordinate errands. The AI assistants employ various language models, including GPT 3.5 Turbo, Llama 2, rule-based applications, Claude.ai 3.5 Sonnet, and GPT-4o, to facilitate the transactions. Here is a combined summary of pages 9 and 10. This research presents two use cases demonstrating the capabilities of Open Value Network, OVON, in facilitating seamless conversations between humans and AI assistants across various domains. In the first use case, a human user, Emmett, interacts with his general AI assistant, Cassandra, who in turn connects him with specialized AI assistants at different service points, including a florist, hardware store, Thai restaurant, and post office. This scenario showcases the efficient management of tasks by these AI agents, independent of the underlying large language models, LLMs, and AI technologies deployed. The sequence diagram in Appendix C, Sequence Diagrams, on page 21, Figure 7, illustrates the OVON conversation envelope messages exchanged between the different agents. The second use case involves an experiment providing conversational AI chatbot support to Estonian citizens. In this scenario, various AI assistants collaborate to provide support for a human user, Lee, who needs assistance with literature research. The AI assistants are characterized by distinct roles, different technologies, and AI capabilities. Lee interacts with Yuri, the front-end AI assistant, who then connects her with specialized AI assistants, Andres and Kaya, to facilitate her research. The conversation involves the exchange of information, including ISBN numbers, book titles, and URLs. The AI assistants utilize different LLM technologies, including GPT 3.5 Turbo, Mistral 7B Instruct v0.3, and Hugging Face 4, Zephyr 7B Beta. Both use cases highlight the potential of OVON in enabling efficient and seamless collaboration between humans and AI assistants, transcending specific AI models or frameworks. Here is a combined summary of pages 11 and 12 of the research paper. The proposed framework for conversational AI agents enables coordination and specialization among agents, independent of the underlying large language models and conversational AI technologies deployed. This is illustrated in the second use case, where Yuri coordinates with Andres to identify the appropriate assistant, Kaya, to provide information on books by Lydia Koitala. The OVON sequence diagram in Appendix C, Sequence Diagrams, shows the exchange of messages between agents. The framework's ability to provide coordinated, specialized support is versatile and adaptable, and can integrate various technologies to meet specific user needs. Future enhancements include representing multimodal interchanges among agents, supporting multi-party conversations, and exchanging background information and context. To address conversational AI security, ethics, and accountability, additional enhancements can be considered, such as an enhanced authentication, authorization, and accounting framework, bias mitigation mechanisms, transparency guidelines, ethical interaction protocols, accountability tracking, and sensitive data redaction and encryption. These enhancements will improve the security, ethics, and accountability of conversational AI platforms. The proposed approach based on open APIs for agentic natural language multimodal communications offers significant advancements in enabling independent conversational assistants to collaborate. The key benefits include loose coupling of assistants, flexibility, ease of integration, and agnosticism to underlying technologies. The approach imposes minimal requirements on cooperating assistants, simplifies communication between assistants, and enhances versatility in handling user requests. The OVON specifications and sandbox provide an open repository for replicable and accessible conversational AI assistants. Incorporating the proposed advancements into the interoperability specifications will elevate the capabilities of conversational AI platforms in managing security, ethical interactions, and accountability, making them indispensable tools in a technology-driven future. The authors express gratitude to the Open Voice Interoperability team for their contributions to the development of interoperable standards. The paper references various sources, including the Stanford Encyclopedia of Philosophy, Springer Nature AI Ethics, and the W3C recommendation on multimodal architecture and interfaces. The authors also acknowledge the work of the Open Voice Interoperability team, specifically the development of the Interoperable Conversation Envelope Specification, the Interoperable Dialogue Event Object Specification, and the Assistant Manifest Specification. These specifications aim to provide a standardized framework for conversational AI agency. The paper highlights the importance of interoperability in conversational AI, citing the need for a standardized framework to facilitate communication between different systems. The authors reference the work of Gosmar, who proposed an on-life evolution model for conversational AI agency, and the concept of conversational hyperconvergence. The interoperable conversation envelope specification is discussed in detail, with references to the invite event, utterance event, buy event, request manifest event, publish manifest event, find assistant event, and propose assistant event. These events are designed to facilitate communication between different systems and enable seamless conversation flow. The authors also mention the Open Voice Trustmark initiative, which aims to promote trust and security in voice-based interactions. Additionally, the Open Voice Sandbox repository is referenced, which provides a platform for testing and development of interoperable voice-based applications. The paper concludes by referencing the Bureaucrat Virtual Assistant, which is based on artificial intelligence, and the interoperability initiative of the Open Voice Network. The authors emphasize the importance of standardized frameworks and specifications in enabling seamless communication between different systems and promoting trust and security in voice-based interactions. Overall, the paper highlights the need for standardized frameworks and specifications in conversational AI, and the importance of interoperability in enabling seamless communication between different systems. The authors reference various sources and specifications, and emphasize the importance of trust and security in voice-based interactions. The provided pages detail the structure and implementation of a conversation envelope object, which is a key component in the Open Voice Network's OVN, Universal APIs for voice interoperation. The conversation envelope serves as a standardized format for encapsulating voice conversations, enabling seamless communication between different voice platforms and services. The conversation envelope object structure, as outlined in Listing 1, includes essential components such as the schema version, conversation ID, sender information, and events. The events are further divided into types, each with its own set of parameters. This structure allows for the capture and transmission of various voice interactions, including utterances and whispers, in a standardized manner. Listing 2 demonstrates a practical application of the conversation envelope by showcasing an HTTPS POST request example. This example illustrates how the conversation envelope can be used to send an utterance and whisper event to a smart library AI assistant, which specializes in author and book information. The request includes a conversation ID, sender details, and the event's parameters, highlighting the flexibility and versatility of the conversation envelope format. In conclusion, the conversation envelope object structure and its implementation, as described in these pages, provide a comprehensive framework for standardizing voice conversations across different platforms. This facilitates efficient communication, enhances interoperability, and promotes the development of more sophisticated voice-based applications and services. The conversation envelope JSON post response example illustrates the structure of the data exchanged between the smart library AI agent and the client. The response contains a schema version, conversation ID, sender information, response code, and a list of events. In this case, the event is an utterance with parameters including the speaker ID, start time, and features such as text and tokens. The text feature includes the response provided by the AI agent, which in this example is information about the book, Harry Potter and the Philosopher's Stone. The response code is 200, indicating a successful request. The conversation ID and sender information are also included, providing context for the response. The utterance event is a key component of the conversation envelope, as it represents the primary means of communication between the AI agent and the client. The assistant manifest object structure example provides a detailed description of the smart library AI agent's capabilities and metadata. The manifest includes identification information, such as the service endpoint, organization, and conversational name. The service name, role, and synopsis provide additional context about the AI agent's purpose and functionality. The capabilities section of the manifest lists the AI agent's keywords, languages, descriptive texts, modalities, and content type. In this example, the AI agent is capable of providing information about books and authors in English, ENIS, and supports text-based modalities. The content type is specified as application, JSON, indicating that the AI agent responds with JSON formatted data. The manifest provides essential information for clients to discover and interact with the smart library AI agent. Here is a combined summary of pages 19 and 20. The conversation envelope JSON post request example, as shown in listing 5, demonstrates a request manifest event sent to a smart library AI assistant specialized in author and book information. The request contains essential information, including the conversation ID, sender details, and event type. The sender, identified by the URL https://somebot.com, initiates the request to the smart library URL, triggering the request manifest event. In response to the request manifest event, the smart library AI assistant generates a JSON response, as illustrated in listing 6. This response includes the publish manifest event type, which conveys the AI assistant's capabilities and identification information. The identification section specifies the service endpoint, organization, conversational name, service name, role, and synopsis of the AI agent. The capabilities section outlines the keywords, languages, descriptive texts, modalities, and content type supported by the AI agent. Notably, the AI agent specializes in providing information about books and authors, supporting keywords such as books, authors, ISBN, and editors, and operates in the ENIS language. The descriptive text highlights the AI agent's capabilities, and the modality is limited to text-based interactions. The content type is specified as application JSON, ensuring seamless communication between the AI assistant and the requesting bot. The OVON universal APIs facilitate this interaction, enabling the smart library AI assistant to respond to the request manifest event and publish its manifest. This exchange demonstrates the effectiveness of the OVON universal APIs in facilitating conversations between AI agents and bots, enabling the seamless exchange of information and capabilities. Here is a combined summary of pages 21 and 22. The appendix presents sequence diagrams for two scenarios, showcasing the interoperability of AI assistants in distinct settings. Figure 7 illustrates the interoperable AI assistant scenario for errands, which demonstrates the seamless interaction between various AI systems to facilitate task completion. The sequence diagram highlights the sequence of events, starting with the user's request to perform an errand, followed by the AI assistant's processing and delegation of tasks to other AI systems. The diagram showcases the standardized communication protocols and interfaces enabling the interoperability of AI systems from different vendors. Figure 8 presents the interoperable smart library AI assistant scenario for citizens, which depicts the integration of AI-powered services in a smart library setting. The sequence diagram illustrates how users can access and utilize various AI-driven services, such as book recommendations and language translation, through a unified interface. The diagram emphasizes the role of standardized APIs and data formats in facilitating the seamless exchange of information between AI systems. Both sequence diagrams can be generated by running the sandbox environment available in the provided repository, allowing researchers to replicate and extend these scenarios. The interoperability of AI assistants is facilitated by the adoption of standardized protocols and interfaces, enabling the integration of AI systems from different vendors and domains. These scenarios demonstrate the potential of interoperable AI assistants to enhance user experiences and improve the efficiency of AI-driven services in various settings. The presented sequence diagrams provide a detailed visualization of the interactions between AI systems, highlighting the complexity and feasibility of achieving interoperability in real-world applications.